Today's video on section 4 is on Avogadros Law, or Principle, and the ideal gas law. So, Avogadro's Principle states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Okay, it's the same Avogadro from Avogadro's number, right, the 6.02 times 10 to the 23rd particles per mole. Same guy, and what he says is that essentially, even though all gas atoms aren't technically the same size, we can assume they are. Right? We can assume that all gas atoms are the same size. Obviously, something like helium is much smaller than something like carbon dioxide. However, right, given their relative size compared to the volume of the container, the differences in size are negligible. Basically, the gases are so small relative to their containers that the difference between one gas and the other gas is, we can forget it, it's negligible. So we don't have to worry about what gas is what when we're trying to calculate the number of moles. So far, the variables we've talked about are pressure, volume, and temperature. Now we're going to introduce moles into these equations. So we should always assume that if you have 1 mole of any gas, it will always occupy the same volume if the temperature and pressure remain constant, right? If T and P remain constant, then we should have the same volume of 1 mole of any gas, which is actually really convenient. It doesn't matter what the gas is made out of. As long as it's a gas and it's at the same volume and temperature, or same temperature and pressure, it'll have the same volume. For our purposes and for the purposes of the problems coming up here, we are going to oftentimes refer to things at STP. Okay, so if you see that, right, at STP, what that means is at standard temperature and pressure. So anytime you see that information, these are the values that you would have with that. The temperature, okay, is technically 0 degrees Celsius, but since we have to have things in Kelvin, that should be 273 Kelvin. And the pressure at STP is, right, 1 atmosphere, okay? And we are going to have that in atmospheres. The problems coming up today, unlike the ones in the past, do require very specific units. So if you are given units with the wrong unit, you're going to have to convert it before you plug it into the equation that we're going to learn. Okay, so going back to the all gases are going to have the same volume at the same temperature and pressure. So if we go at STP, standard temperature and pressure, and I have 1 mole of any gas, doesn't matter if it's helium, carbon dioxide, oxygen, whatever, 1 mole of any gas at 273 Kelvin and 1 atmosphere of pressure fills a volume of 22.4 liters. That's actually quite a bit of size there, right? You might think of this like, how big is that? It's 11 2-liter bottles. Okay, so you know what the size of a 2-liter bottle is. It'd be like a little over 11 of those. So it's fairly sizable. It takes up quite a bit of space for 1 mole of a gas at STP. So what we can do, though, is write that as a conversion factor, 22.4 liters per 1 mole. Okay, so if we're at STP and only standard temperature and pressure conditions, for every 1 mole of gas, you have 22.4 liters. We can also use that as a conversion factor, meaning I could write that as 1 mole of a gas is also 22.4 liters. Okay, so that will be helpful to you. You can kind of use that as a shortcut in some of these problems. Okay, so real quick practice problem using that information. This says, calculate the volume that 2.00 kilograms of methane gas will occupy at STP, at standard temperature and pressure. Okay, so we have this information that it's 22.4 liters, right, volume per 1 mole of gas. So if I can figure out how many moles of gas this is, I can figure out how much space it's going to take up. Okay, well, I can figure out how many moles there are of this by taking the grams, which would be this many here, 2,000, right? Multiply that times 1,000, divided by the molar mass. So let's do that. Moles of methane, by the way, is CH4, if you don't remember. Moles here will be 2,000 grams divided by 16.04 grams per mole. And that's going to give us, with 3 significant figures, 125 moles of CH4. And from that, if I want to know how much space it's taking up at STP, I can take the 125 moles of CH4, and if I use this bit of information right here and multiply it, I'm going to get my units to cancel. 22.4 liters for every 1 mole of gas. Well, CH4 is a gas, right? So my moles of gas units would cancel. If you take 125 times 22.4 and round that to 3 significant figures, we are going to get something in the neighborhood of 2,790 liters. Okay, that's a lot of space. Okay, just for reference, right? That's like 1,300, almost 1,400 2-liter bottles. So that's quite a bit of space for only 2 kilograms of mass. That's like roughly 5 pounds. So 5 pounds of air is taking up like the volume of an entire room. So what's the relationship between Avogadros Principle and the combined gas law? Well, the combined things that we have talked about P1 V1 over T1 equals P2 V2 over T2. If we rewrite this, what this means is that we actually, these are constants, right? P1 V1 over T1 is equal to some constant, and P2 V2 over T2 would be equal to the same constant. So if we rewrite that into PV over T, just doesn't matter which one, initial or final, because they're going to be the same thing, and just say that equals some constant, let's see where that leads us to, see what we can do from this. Okay, so if we add PV over T, well, where could we put Avogadros Principle in here? Using Avogadros Principle and N for the number of moles. So N is the number of moles, right? That's what that is. And you guys know how to calculate moles given mass. For number of moles, N is for number of moles. This could be rewritten as PV over N times T. So where does moles fit into the equation? It fits in on the denominator, right next to temperature. PV over N times T is equal to some constant. So now, pressure times volume divided by moles times temperature gives us a constant. This constant has a value, and it's called the ideal gas constant, R. It's a capital R. And that value is always the same. So this value here, no matter what, this is actually really remarkable, of all things considered here in nature, that the pressure times the volume of something divided by the number of moles times the temperature always gives us the same number. Kind of remarkable. If the pressure in atmospheres, if the pressure is in atmospheres, R is equal to 0.0821, and the unit on this is actually kind of important. Liters times atmospheres divided by moles times Kelvin. 0.0821 liter atmospheres per mole times Kelvin. And what we're going to use is that in place of where the word constant is. So if we substitute R in for where the word constant is, I have PV over NT, okay? And if I rearrange that, okay, and get rid of all my denominators, I wind up with this equation down here, PV equals nRT. This is the ideal gas law. So if there's one thing I don't want you to forget from your entire chemistry, it's this equation, PV equals nRT. Sometimes this equation is called PUVNERT. That helps you remember the order of the variables. PV equals nRT. Something of note here, pressure has to be in atmospheres this time, so you have to convert it if it's not. Volume must be in liters, and you have to convert it if it's not. N should already be in moles. Okay, that's what that is. R is 821 liters times atmospheres over moles times Kelvin, and T must be in Kelvin like it usually is. So this is the first time that we've had an equation where pressure and volume must be in these units, atmospheres and liters. And the reason is because of what the constants values are. If I change these, I'd have to change the value of the constant. So we're not going to do that. We're just going to convert pressure to atmospheres and volume to liters if it's not already that way. All right, this says calculate the number of moles of ammonia gas contained in a 3-liter container at 300 Kelvin with a pressure of 1.50 atmospheres. So here's my equation, PV equals nRT. R is 0.0821 liter atmospheres per mole Kelvin. All right, based on the other information given to me in the problem, I have V is 3.00 liters. T is already in Kelvin, so that's convenient. And pressure is 1.50 atmospheres. The variable I'm trying to solve for here is the number of moles. So I'm trying to solve for N, right? That's the one that I don't know. So if I take the PV equals nRT equation and get N by itself, that means I need to get rid of RT on the right side. So I'm going to divide by RT on the left side. And I get N is equal to PV over RT. And if we plug those values in, we have 1.50 atmospheres times a volume of 3.00 liters divided by R is 0.0821 liters times atmospheres over moles times Kelvin, and temperature is already in Kelvin, 300 Kelvin. You can actually see what happens to the units when I do this. Atmospheres cancels, liters cancels, Kelvin cancels, and since the moles are the denominator of something in a denominator, it actually flips up to the top, and that would give us the unit of moles. So that's why R has the units that it has. And if I plug all this in, 1.50 times 3 divided by, make sure you put the whole bottom in parentheses, otherwise you're very liable to make a mistake. 0.0821 times 300 to 3 significant figures. This is 0.183 moles. Okay, so that's that answer. If the question asks you how much did it weigh or what's the mass of it, you just multiply times the molar mass of ammonia. So you can do that as well. You can figure out how much that actually weighs, which is kind of neat. Okay, one practice problem from the homework. We're going to do number 1 together here. This is on your 8-4 worksheets. Number 1 says a gaseous sample occupies 43.5 milliliters at negative 25 degrees Celsius and 0.405 atmospheres. What volume will it occupy at STP? So we have kind of 2 sets of conditions here. We have an initial set of conditions, which is this group right here, and a final set of conditions, which is STP, and I'm solving for volume. The first set of conditions, it gives me a volume, it gives me a temperature, and it gives me a pressure. I'm solving for the number of moles. The second one, it tells me what the temperature and the pressure are because it says STP, so that's 0 degrees Celsius and 1 atmosphere of pressure. I know N because if I solve for N over here, it's the same as N over here, so N from the first part of the problem, and then I can just solve that for V. So, and actually you can really shortcut this using the combined gas law because the number of moles don't change, it remains constant, but I want to show you that we can use the ideal gas law to solve this. So, a couple things. First of all, we got to make sure we convert stuff into the units we need for this problem. Milliliters has got to be in liters, okay, and temperature has to be in Kelvin. So we have to do that first. If I take PV equals nRT, I need to solve for N, right, for the first set here. So I'm going to divide by RT on both sides. N is PV over RT, okay, and pressure is 0.405 atmospheres. Volume is 0.0435 liters. Divided by R, which is 0.0821 liter atmospheres per mole times Kelvin, and T is 248. Okay, this would give us, let's plug this into a calculator, 0.405 times 0.0435 divided by 0.0821 times 248, and we get a sort of small number here. I get 0.000865, which is the number of moles. And that value I can also use here, right? So I can plug that into a second set of conditions. Okay? And there's actually a couple things we can do to shortcut this problem, so I'll show you both of them. But part 2 here, once again, PV equals nRT. This time, over here, I need to solve for volume. So let's get volume by itself. Divide both sides by P. Volume is nRT over P. So it's equal to 0.000865 moles times R, which is always a constant, 0.0821, times T. Well, at STP, it's 0 degrees Celsius or 273 Kelvin. Okay. All that divided by pressure, which at STP is 1 atmosphere. Okay, so 0.000865 times 0.0821 times 273. Okay, and this gives us 0.0194 liters. Okay, or if we wanted to make it comparable to the number given in the original part of the problem, that would be 19.4 milliliters, right? Either one of those answers I would take. What we could also do, instead of having to plug this back into the ideal gas law, which works, we learned a shortcut earlier. We'd said that at STP, 1 mole of gas takes up 22.4 liters of space. So I could have also done 0.000865 moles times 22.4 liters for every 1 mole of gas, okay? And that should give us the same thing, okay? Yep, we get 0.0194 liters, which is the same thing as what we had previously, 19.4 milliliters. So we could do that. There's also one final option. Because the number of moles of gas stays constant, so N is constant, right, in this problem. If I set up my equation to look like this, right, if you go back and look at my setups, this would work. Well, in this case, N1 is equal to N2. So if that's the case, they would actually just cancel out, and what I'm left with is the ideal gas law, or sorry, the ideal gas law, the combined gas law. And I only need to solve for V2. So V2 would be P1 times T2 times V1 divided by, let's see here, P2 times T1. Right, and if I plug all that in from the entire problem up there and use the numbers over here as 1 and these as 2, it will prove to you that this works as well, right? So this would be like P1 right here, T1, V1. So that would be 0.405 atmospheres. T2, okay, would be 273 Kelvin. V1 is 0.0435 liters. All of this divided by P2, which is 1.00 atmospheres, times T1, which is 248 Kelvin. Okay, and I'm going to do it on the calculator just to make sure that it works. 0.405 times 273 times 0.0435 divided by, well, 248, right? And we get 0.0194, right? So that should look very familiar. So there's actually several ways to solve this. But since this is the ideal gas section, that's what we would like you to use to solve it, right? Using this whole method right here, plugging it in, solving for N, plugging that value into PV equals nRT with a new set of conditions, and we got the answer. You could find the number of moles and then just multiply it times 22.4 liters per mole, because, well, that also gives you the answer. Only at STP can you do that, though. You can't do that at any other conditions. Or because the number of moles stay constant, you could use the combined gas law. So, there you go.